Hey guys, welcome back to my channel where we explore interesting math problems. Today, we'll be looking at a geometry problem from the 2021 Canadian Math Contest Cayley, which is for 10th graders. The contest has 25 questions, with the questions ordered from least to most difficult. The question that we'll be looking at today is question 24, making it one of the hardest questions on the contest. So the question reads, a cube with edge length 8 is balanced on one of its vertices on a horizontal table such that the diagonal from this vertex through the interior of the cube to the furthest vertex is vertical. When the sun is directly above the top vertex, the shadow of the cube on the table is a regular hexagon. The area of this shadow can be written in the form a square root b, where a and b are positive integers and b is not divisible by any perfect square larger than 1. What is the value of a plus b? So to better understand this question, let's start with some visuals. Here we have the cube balancing on one of its vertices, with the vertices diagonal from this one being its furthest vertices. And we also have the sun shining directly on top, producing this shadow that's supposed to be a regular hexagon. However, because the sun is shining directly on top and not at an angle, this means that the shadow will be directly under the cube, which means whatever you see directly from the top of this cube will be what the shadow will look like. And in this case, it would look like this. For more clarity about both of these visuals, let's look at a real-world example. So this would be what a side view would look like, with the bottom vertices and the furthest vertices having a diagonal straight up between them. Although this picture is a bit slanted, it is supposed to be perfectly straight up. And this is the top view. And you can kind of see how it's supposed to be a regular hexagon. Although the picture I took wasn't so perfect. So I hope this makes more sense now that you've seen what the cube would look like in real life. Let's get back to our question. So now that we know that the shadow is equal to the area of this, the question then becomes, what is the area of this shape here? Let's first label the vertices, and because we know each side is 8, we can label that too. And we can draw these lines to make the area easier to solve. This is because you can notice how each of these small triangles is half the parallelogram, which means that this bigger triangle is half the area of this hexagon. Now, to solve for the area of this triangle, we can first find its side length. And you might be tempted to say that it's 120 degrees because it's a full round 360 degrees divided by 3, and then you could use the law of cosine to find AE, like this, and then conclude that the side length of this equilateral triangle is 8 square root 3 and carry it on from there. Unfortunately, that's wrong. Let's backtrack a bit to understand why that wouldn't work. To begin, even though this looks 2D to us, we have to remember that, ultimately, this is still a 3D shape, and that we're just viewing it from the top to make it look 2D. And this parallelogram, AFEO, for example, would actually look like this instead, if viewed straight on instead of from an angle. And this makes sense, because each side of the cube is a square. And you can label these side lengths as 8. Although that may seem like there's no difference from our previous calculations, the reason why we have to look at it as a 3D shape is because if we were to actually just take the 2D shape, this side length wouldn't even be 8. Even though the original side length of the cube is 8, because the top view means viewing it at a slanted angle, the side length, which is the 2D projection that you would see, would actually be less than 8. This is why using the value of 8 and then treating it as a 2D shape messes everything up. And so here's the game changer between viewing this as a 2D shape and as a 3D shape. Instead of seeing this as 120 degrees as before, you see that this is actually 90 degrees. And that changes the calculation completely. Instead of using the law of cosine to find the length of AE, you will use the Pythagorean's theorem since we have a right triangle. And from there, get that AE equals 8 square root 2. And we can label it here so we don't forget. Okay, so now that we have avoided calculating the wrong value for AE, How can we find the area of this equilateral triangle? Let's erase everything else first and consider an equilateral triangle with an unknown side length s. We know that all three angles will be 60 degrees. And let's draw the altitude, which cuts angle A in half. So each angle here becomes 30 degrees. And let's label this part M. So EM would be S over 2. And using your knowledge of the properties of a 30, 60, 90 triangle, or just using trigonometry, you will know that AM is square root 3 over 2 times S. We know that the area of this entire triangle, AEC, is twice of AEM, because AEM and ACM are just mirror copies of each other. And we know that the area of triangle AEM is 1/2 times the base S over 2 multiplied by the height square root 3 over 2S. Simplifying, we get square root 3 over 4S squared, which would be the general equation for finding the area of an equilateral triangle given the side length S. Back to our question, we can use the equation we've just found and substituting the side length S with AE instead. And plugging in what AE equals, we get 32 times square root 3. And since we've previously established that this entire hexagon ABCDEF is twice of triangle AEC, we just multiply by 2 to get the area, which would be 64 times square root 3. And so we have the area in this A multiplied by square root B form. And since the question is looking for A plus B, we plug in what we got to get 67, which is our answer. So I know this one's a bit longer, but I hope that the diagrams and the real-life pictures helped you to better understand this geometry problem, and I hope to see you next time for more.